that is in solving relations, but well, we are not extending to there is specific areas of application with respect to your areas of concentration. But what I'm doing is what discrete mathematics does is to set a basis so that when now you get to your areas of concentration, you should be having an idea. Now, we told you that the nature of an object is expressed by its relationship with other objects. You see, the nature of an object is expressed by its relationship with other objects. Thus, you told that a relation, this is what a relation does. A relation binds together two objects of a particular class according to the same rule. According to some rules, this one should be some rule, not according to some rule. Sorry, according to some rule. And you told me that a relation is denoted by R. Mathematically, if A and B, that is why you can see, we talked about sets last time, and it was very important to have a reminder of what sets are. And there are quite a number of, look at even the Cartesian product. You notice that, yes, we talked about Cartesian product. You can see in this case, it is coming in handy. So it is important that you have that at your fingertips. And you told me that mathematically, if A and B are two sets, then a relation from A to B, a relation from A to B, a relation, just a moment there, okay. I thought maybe there is a concern. I'm not seeing any. Okay, a relation, you told me that then a relation from A to B, look at this, is a subset of the Cartesian product. Oh, yes. Meaning, when you talk about the Cartesian product of these, of course, just remember, how do the elements of a Cartesian product look like? Just to remind you that the Cartesian product of B is equal to a set AB, such that A belongs to A and B belongs to B strictly. BA is not, don't forget, BA is not in the Cartesian product of A cross B. So the order in which we present the sets is very important, because you see, as to why we say that BA is not in AB is because the element B is not in A and the element A is not in B. It is that A is in B and B is in B. So it is important that you have that, you remember that. So we told that then, you see that a relation, in fact, is simply a subset of that Cartesian product. It means that it depends on the rule at hand. The rule at hand dictates the members of that relation, and therefore the members of that relation are not likely to be the entire set of the membership of the Cartesian product. And look at this here. That is, a relation, as you can see here, is a set of ordered pair x, y, where x is in A and y in B, but that is not enough. We have x is R related to y. This is what is written. This is what this indicates. It represents, or rather it denotes, either indicates or denotes, x is R related to y. X is R related to y. See that? For us to have a better understanding of that, let's see this example. We consider the set A whose elements are 2, 3, 4, and 5, and R to stand for is the rise of. So we see in this case, indeed, this is true, but again, wait. When we say there should be, excuse me, let's see that this one doesn't make sense. We must be very careful here. This 2, 3, this one doesn't, this doesn't end there. This continues all the way to, let's talk of up to 16. There is an error there. There is a type of error, typing error there. That we have look at this. We have 2, 3, 4, 5, 6, 7, 8, all the way to 16. And we told that R stands for is thrice of. Then we see it is 2. 6 is thrice 2. So even another one here. These ones are not enough. If anything, yes, there is a typo here, and this one is important, right? This one is important that it is emerging even during the lecture. There is an error here. We see here. Look at this. 6 is thrice 2. 3 is 9 is thrice 3. We have 12. Is it? Yes, is thrice 4. And then now we have 15 is thrice 5. And this, if you look at this one is a subset of the Cartesian product of A and A. That is one A and itself. And as you can see here, as to why, look at this and be very keen. 16 is, 18 is thrice 6. But you notice that 18 is not in here. You see, A consists of the elements 2, 3, 4, 5 to 16. Had we, let's say, suppose we stopped at 2, 3, 4, 5 only the way it had been given here, then we could have had only 6 is thrice 2 without going beyond that. We could have just add this 6 to be that the membership of that relation. But now in the case of extending this all the way to 16, then you notice in this case that there is something missing here. This one is 9 is thrice here. 9 is thrice 3. So we have again here 9 is thrice 3. And we see here the brackets we use are the ones that represent an ordered pair. So we have 9, 6, 2, 9, 3, 12, 4, 15, 5. And those ones that this one makes up a subset of the Cartesian product of A and A. The Cartesian product of A and itself consists of many other pairs apart from these 4. And that is why we consider this to be a subset of that Cartesian product. And now we go now and talk about what we call domain and range of a relation. What do you mean by that? Let's go to that. We told, of course, we consider R to be a relation defined from A to B. That is, R, of course, is a subset of the Cartesian product of A and B, the way we've said here. The domain R, denoted R, is the set of elements of the first set, this one, that are related to some element, not only all the elements of A, that are related to some element of B. Like in this case, in our example here, these are the members of the domain of R. 6, 9, 12, and 15. Wherever, Brian, kindly please, can you mute, Brian? Okay. So we see the domain in that case consists of 6, 9, 12, and 15. The range consists of the members of B, 2, 3, 4, 5. That is it. You can see that. Look at this. You can see this is the domain, the set of members of X, such that X, Y is in the relation. And you can see these ones are in R. Remember, our relation in this case is this one. This one is R. And you notice that The ones that are in this relation are 6, 9, 12, and 15. That is the domain. And the range consists of 2, 3, 4, 5. So I know you did the calculus 1 last semester. And when you did calculus 1, there is something that no. I think you are doing calculus 1 at the moment, right? It is this semester that you're doing calculus 1, and you've done functions. And what you've gotten to know about functions, you've talked about domain and the range of functions. Now, also, when you're talking about a relation, we have also what we call the domain and the range of a relation. And the domain is simply the set of members of the first set, so long as that X is found in the pair that is inside that relation. The domain is the set of Y. This one should be Y. Let me see. Y. This one should be Y. Yeah, there are some typing errors there. That is, it should be Y, where Y is in B. And that Y is obtained from that pair that is inside the relation. Like in this case here, you see this one is Y, 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 Y. And all these are 2, 3, 4, 5. Those ones make up a set, and that is the domain of that relation. You notice something, and I think this is something that you've seen. The domain of a relation is a subset of A. Look at this. 6, 9, 12, and 15 is a subset of this set. 2, 3, 4, 5, all the way to 16. And that is why you can see in the earlier case, as having it this way, I told you that there is an error, because then if we had 1, 2, 3, all the way to 5, then 9, 12, even 6 is not in here. It's not a subset of 6, 9, 12, and 15. That set with 6, 9, 12, and 15 is not a subset of A. Yeah, so there is the same case again here. The range of R is a subset of B, indeed. But now in this case, you see it is the Cartesian product of a set and itself. And that is why we're referring to one and the same set there. But there will be some other cases that we shall come across ahead that entail two different sets. And these ones will be there in a moment. But before that, let's deal with this example. We have with 1, 2, 3, 4, 5. This is the set A with the brackets used here should be here. Look at that. I think I should save this. Yes, let me save this work so that I can correct it before sending to you. Yeah, that is okay. So we define a relation A to A such that A is related to B if and only if A is less than B. Look at this. For every pair that is, for every pair, check. Yes, by the way, no, for every pair, let's get this clearly. This one should be for every pair that is in A cross A, the Cartesian product of those ones. Yes, are you seeing that? This one should be the Cartesian product. You see, this is another pair, and this ordered pair should be in the Cartesian product of A and itself, because we're talking about only one set. And you are asked to find the domain of R and the range of R. So if we're asked to find that, then you see the condition is that whenever you have a pair in A cross A, that pair must be that it consists of elements. The first one must be less than the second one. So if we have both pairs, then done. Yes, Ochem, you've raised your hand. Yes. Ocheng Okok. Let's continue. Now, here we see we have the pair 1, 2. 1 is less than 2, that is okay. 1, 3 is, yes, 1 is less than 3. 1, 4. 1, 4 is also less than 4. 1 is less than 4. 1, 5, that is why we have that. Then 2, 3. 2, 1 is not, because 2 is greater than 1. And the condition is that the first one must be less than the second one. So we shall have 2, 3, 2, 4, 2, 5, and then we go to 3, 4, 3, 5, and then 4, 5. Those are the members of that relation. And the domain, therefore, is 1. We don't repeat members of a set. 1, 2, 3, 4. No, sorry. 1, 1. This one's repeated. 2. This one is also repeated. So we have 2, and then 3. 3 is repeated there. We don't repeat that, and then 4. So that is why we have 1, 2, 3, 4 here. The range is the second 2, 3, 4, 5. This one is repeated. 3, 4, 5 repeated. 4, 5 repeated. 5 repeated. So that is the range. Let's now go to types of relations. We have a number of types of relations, 5 of them. We have what we call a binary relation. When do we say that a relation is a binary relation? We are asked to let A be a non-empty set. What do you mean by a non-empty set? A set with at least one element, and R be the relation in A, or other relation on A. When we say a relation in A, it means that we are having A cross A, meaning that the relation is a subset of, you can see, of A, the Cartesian product of A and A. Then we told that A is binary. It's a binary relation on A. You see, if we're having, that is, now the question is this a binary relation? You see, this one is A cross A. Is this also a binary relation? I think yes. Is this also a binary relation? That you see, that question comes to our mind immediately. Are these two relations, these two examples here, are these two binary relations? And you can see in this case, you're told that symbolically, R is a binary relation if its membership is an ordered pair XY, where X and Y belong to A. Both of them belong to A, and that is true. And X is unrelated to Y. And therefore, this one is called a binary relation. When we're having, that is a set, there is a relation between members of a set and the same set. That is what we have. So therefore, these two are binary relations. And the relation, you realize that it is defined by that, you can see. And the relation in this case is defined by this. It is thrice of, you see, that is it. So those ones are binary relations. Those ones are good examples of binary relations. When we talk about equality relation, we see that we told that the relation R on a given set again here. So it's suggesting to you that when you're talking about this, an equality relation also is a binary relation, because then we're talking about a relation that entails whose members are there is ordered pairs, and these pairs originate from the same set. This R is a subset of A cross A. And we told that this one is called an equality relation if R is the set of elements of A cross A, where an X is equal to Y. You see that a good example here. This one is called an identity relation also. It's also called either equality relation, but this one is no more common. An identity relation on A, and you notice that then this one becomes an identity relation if X and Y are the same. And in this case, we have this example here. If we take A, B, there is a set of elements with A, B, C, whose elements are A, B, C. Then you notice that this one is, you see this R here that consists of AA, BB, CC is what we call an identity relation. If we talk about, let's say, B, which consists of, let's say, 1, 2, 3, 4, then the identity relation on B, you see, is this one, 1, 1, 2, 2, 3, 3, You see, and then 4, 4. Where is it? There is an identity relation on B. A universal relation, if we obtain all ordered pairs of A, simply this is the Cartesian product of two sets. What we did even last time. If we obtain the Cartesian product of any two sets, and you exhaust on all members, of course, obtaining the Cartesian product, you must obtain all members, like this. If we have A to be equal to, let's say, 2, 3, 2, 4, no, let's say 3. Sorry. No, that is not how we write the members of a set, sorry. We have 2, 3, and then let's say we have B to be equal to, let's say, A, B, C. Then this is the universal relation. The universal relation is simply, it is simply the Cartesian product of A and B. And in this case, we have 2A, 2B, 2C, and then we continue 3A, 3B, and then the last one, the ordered pair 3C. This is what we call the universal relation. So if you're asked to find if A is equal to, I can rephrase this to come in the form of a question. If A is equal to 2, 3, and B is equal to the set with the elements A, B, C, find the universal relation of A and B. Void relation in that case is what we call the null relation, or the null, yes, the null set. And you find that in this case, there is no, it is simply the empty relation. That is what we call the empty relation. It doesn't have any ordered pair. We have the last relation, and the last relation in that case is what we call the inverse relation. The inverse relation reverses what a relation does. Like in this case, the inverse relation of this relation is that relation with the elements 2, 1, 3, 1, 4, 1, 5. You see, so R inverse in this case, if we were to talk about this one, R inverse, the inverse relation will be 2, 1, 3, 1, 4, 1, and that continues that way to the end, all the way to 5, 4. That is the inverse relation, the inverse relation of this. And that is exactly what we're being told here. It's a set from a set A to B. If R is a relation from A to B, then the relation R from the set B to A back to, you see, from B to A is defined as the inverse relation. And this is denoted, or rather, well, symbolically, or it is denoted, oh yes, it is denoted R inverse. And symbolically, we have it here. And you can see this, such that there is such that here, or either that, or we use colon if you remember. This one represents such that, or this one. Okay. And you told that the inverse relation is greater than, is the relation less than, just like what we've done here. See, look at this one. We told here, if and only if A is less than B. But now the inverse relation of this is if A is greater than B. That is the inverse relation of A is less than B. This R is defined by is less than. But now our R inverse will be is greater than. And that is exactly what we can see here. 2 is greater than 1, 3 is greater than 1, right? And so on. We have an example here, a good example. We let A be this, our B is that, and we define the relation R from A to B by less than, and in this case, our R is this, 3 is less than 4, 3 is less than 7, 3 is less than 8, that is okay. 4 is less than 7, 4 is less than 8, that is it. And then finally 7 is less than 8, and that is it. These are the members of that relation. R inverse, therefore, will be simply 3, 4, 3. You can see that 4, 3, 7, 3, 8, 3. You see, 4 is greater than. This one was less than. This one is greater than. 7 is greater than 3. 8 is greater than 3. 7 is greater than 4. 8 is greater than 4. 8 is greater than 7. And we observe, therefore, that for each of the pairs, are related by the relation is greater than, and that is exactly what I've mentioned there. We have what you call a restriction of a relation to a set. How do we restrict a relation to a set? Let's have there is a background to this. We are asked to let R be a relation on a set A and B. And of course, let's see this. Oh, no, there is something here. R is a relation to be a relation on a set A and B. And okay, let's see that. And B is a subset of A, yes. And it's okay, it's quite okay. Let R be a relation on a set. That is okay. And B be a subset of A. Yes, that is it. This one we're saying, meaning members of R will be, in fact, will be a subset of A cross A. Look at that, please. It is the members of R of this relation are members, each one of them is a member of the Cartesian product of A and itself. And we're told that B should be a subset of A. See, every member of B is inside A. Then the restriction of R to B, the restriction of this, which is a subset, of course, its members must be members of the ordered pair A cross A. Of the Cartesian product of A, and itself, whatever A cross A. B is a subset of A. So how do we restrict this relation to B? You see, we obtain, look at this, we obtain the Cartesian product of B and itself. You see, look at that. So we have A, we have an example in this case here. Let's look at this example. And the relation is defined this way, okay? Apparently, it has not been, the definition has not been given. We've been given the members of the relation here. AA, AB, BC, AD, BD, and CD. And then look at this, BD. Indeed, it is a subset of A. Every member of B is inside here. So what we do, we have B cross the Cartesian product of B and itself. You see that one will be BB. And then we have BD. And then, of course, the last one is DB. Right? You see, this is when you're having the Cartesian product of a set and itself, that is when you are allowed to, you see, look at this. This one commutes with this. That is when you are allowed to have that. But if you're having the Cartesian product of a set and another one, you can't do that. You see, this is what I mean. A cross B, if A is in with this one, let's say, let's even have a result. Say 2C. If this one 2C is in A cross B, then C2 is not in A cross B. So you cannot have that flexibility in as far as this is concerned. You can have that flexibility in as far as BDDB, because here we have the Cartesian product of B and B. And you notice that D is also in B, and B is also in that. But in this case, 2 is strictly in A, C is strictly in B. These are two different sets. C cannot be in A, and 2 cannot be in B. Right? So we have that. And now, what do you mean by intersection? You see, we have now the relation. Therefore, now that we have the relation R intersection the Cartesian product of n itself. So we pick this. The intersection of sets refers to the set of those elements that belong to both. So you identify pairs that are here and are also inside here. AA is not here. AB is not here. BC is not here. AD is not here. BD, yes, BD is inside. Okay, so it is actually that is the only one. You can see that is it. CD is not inside here, and therefore that is why you can see. Now there is a restriction of R to B. That is how we do a restriction. So you could be even asked if, let's say, C is equal to, that is, let's say, AC or rather ABC. Yes, maybe we can do that. Under properties, we shall deal with that next time. Let's let me add you one more question here. Suppose here, if an example, if let's say C is equal to ACD, right? Then you're asked to find a restriction of R to C. So what you're supposed to have here is the Cartesian product of C and C. And here we shall have AA. We shall have, yes, AC. We shall have AD. You can see that I'm having AA, AC, AD. If anything, we are having also, look at this carefully. We have, you see, for you to see that clearly, have another C here. We shall have ACD. Maybe you are not seeing that. You see AA, AC, AD, and then now you have CA. Are you seeing that? You have CC, you have CD, you have DA, DC, DD. That is it. So we shall have here CA, CC, and then CD, and then we have DA, DD, no, DC, sorry, and then DD. Now, I've said this only is allowed for you to go back, like here CA, DA. You are allowed for the case where you are only having a Cartesian product of a set and itself. If it is a Cartesian product of a set and another one, that is not possible. That cannot work. So we have now the intersection of this and R. You see, our R is this. So what we need to do is to identify those elements that are common between the relation and CC. You can see one of them. If I can use different ink, let me use blue. Look at that. AA is there. Let's see here. AB is not here. Of course, it cannot be. BC is not there because we don't have B. AD, yes, we have AD. And see that AD is here. We have BD. Let's see, yes. No, we don't have B, and therefore there is no BD. And then we have CD. CD, I think we have it somewhere right here. And therefore, the restriction of R on C is equal to AA, AD, and then CD. Perfect, and that is it. I think we already 4 minutes past the time. I think it will be fair if we leave it there, so that next time when we meet, then we shall pick from there. We shall deal with the types of relations, or properties, not types rather, but properties of binary relation, and get to know exactly what we remember here. We're talking about binary. If you remember what we talked about binary, don't forget that. I think I talked about here binary relation. So we are getting into the finer details about properties of a binary relation. And I think we spare that the next time when we meet. And these properties are three. And once you have those three properties as three, then you come across what you call an equivalence relation. Then so quite a number of times you'll be asked to determine whether the following relation is an equivalent relation or not. Then I think we shall be good enough if we get there. Maybe we can add up some few things, and then we shall be done with relations. We shall cross over to what we call groups and rings, and then now go back to mathematical logic and an advancement of that. And of course, what I gave you last time, I gave you soft thoughts about that. So